Okay, I'm recording, just in case you're curious, and we can come back to this later. So let's take this from the top, and I'm going to leave it in non-present mode just so that just helps out with navigation. So fortunately, we've already been here and done that. So we've set up some circuits to allow electricity to flow. We've been drawing our circuits in a slightly different style, and we've actually been drawing them the way electrical engineers draw them. But as we scroll down, this style does a couple of things that other style doesn't really do for us. And so we're going to learn both ways. So tonight we're just going to take a look at battery, current, resistors and resistances, and a little bit of resistivity. And then we'll talk about the other topics on Thursday night's meeting. Now, quick note, if you've got a pen or a pencil or something like this to write this down, I have a couple of things that are going to be a little bit different. So in my day job, which is teacher and science department head at Essex High School, that we have parent conferences on Thursday night. So I took a leave of, I took a personal leave for an hour. And so my plan is to start at 7, and I'll be doing parent conferences before that. So that's what our plan is. And just make a quick note. So if you're looking for a meeting at 6 o'clock, when you open up the Zoom link, it's going to say 7 instead.
So that's this Thursday?
That's, yep. Night after tomorrow. And then again, away from tonight, that's going to be a hybrid session at Winooski. And I'm really excited. I've got some cool toys. So I'm going to show you some of them tonight. So, all right. Yeah, so we start off with some basic oxidation and reduction. Where's the battery coming from? So Alessandro Volta, an Italian in the 18th century, and along with many other people, were experimenting with this new kind of chemical reaction. And there were, for sure, acids available, weak acids available. So vinegar, is an obvious one. And what Volta figured out is that if you use different kinds of metal and sandwich them between pieces of leather that have been soaked in vinegar, that you can actually figure out a way to apply this to frogs' legs and they would twitch. Because of course we know that the muscle contraction is triggered by an electrical impulse. So Volta he was trying to refine that. He was trying to get the biggest jump out of the frog legs possible, because he wound up going down the road of trying to bring things back from the dead. So his big contribution to science was the beginning of the electric battery. But after that, there wasn't a lot of good science going on. But of course, we know that this is just an oxidation reduction reaction. So carbon zinc is a really common combination of metals to use, and that gives us a potential difference of about 1.5 volts. So if you've ever done a science experiment where you like jab a couple of metals into a lemon or a banana or whatever, it's all the same thing. The difference is that when you jab a couple of metals into a lemon, then you will get a voltage, because we know that voltage is energy per unit charge, but you don't get a lot of current. So remember our analogy in our distribution Amazon analogy is that voltage is like the number of packages per truck, but when you jab 2 pieces of metal into a lemon, you don't get a lot of trucks. So it's not going to be super powerful. So refining this process was the big contribution. And that's why we have volts today. So this battery concept means that it's all chemistry, and that's a big area of research right now. I could get on my political soapbox and talk about how the oil industry suppressed research into batteries for nearly a century, but that's not the place for that. So Yeah, so really up until about 10 years ago, we were still using the same battery technology that your great grandparents were using. And now we're sort of behind because we realize that storing electrical energy is very important. As we try and look at our electrical energy production, we need to be a little more creative because some of the sources we get energy for um, are producing at a time when we're not at peak demand. So we have to mitigate that somehow. And batteries are definitely going to be a part of the solution. So let's take a look at the anatomy of a battery. And so the modern, that's funny. So really what we have is we have a carbon rod that's buried in um, some electrolytes and sort of like a pasty substance that's held together with paper. And then the outside is actually zinc. So it's the outside part that gets oxidated. And usually the zinc is made thick enough so that by the time the carbon is used up, there's still some zinc left. But if that's not the case, with carbon and zinc being the products of the reaction, if that's not the case, and then too much of the zinc gets eaten up, then this package isn't leak proof anymore. So that's where you get the gross batteries from that, you picked up that cool keyboard that you got when you were 5, and then you see it again when you're 10, but it's all messed up because the batteries leaked everywhere. All right. So batteries come in lots of different packages. And I'll share a little bit about those packages with you. And I think we've talked about this a little bit too. So all the carbon zinc batteries have the same potential difference of 1.5 volts. But it's when you put them in different packages, like a 9-volt batteries release 6 1.5-volt batteries. If you want more current, then you can have more batteries side by side in parallel. And if you want more voltage, then you add the batteries one after the other. So we, in our first hybrid lab, we played around with that a little bit. So adding batteries in series gives you a higher voltage, but not more current. But adding batteries in parallel does give you more current. So definition of electric current. Again, fortunately, we've had a chance to front load this concept a little bit, but it's the rate of charge flow. So anything over delta T is always a rate. And this rate can also be expressed as a differential if we were doing calculus. And the SI unit for electric current is what we get when we divide 1 coulomb by 1 second, and that's called an ampere, after a French physicist who did a lot of work in the early 19th century. All right, so when we complete a circuit, we have charges that have potential, and they're ready to go. So the Amazon trucks are at the warehouse and they're all loaded up. And then when we make a connection, then they leave the building and we start delivering packages. Now, one of the big problems with that analogy that I was talking about the Amazon distribution, is that with conducting wires and charges, the conducting wires are already filled with charges. And we just provide a path for them to start moving. So it's kind of like when we throw the switch, it's almost as if the roads are already filled with Amazon trucks. They're just not moving. And then when we complete a path from them, then they start moving and they actually start delivering packages instantaneously or delivering energy instantaneously. All right, here are some silly ways to not make a light bulb light up, except for the one on the right that works. And then we're also stuck in this world where charge is flowing from positive to negative. And we can blame this one on Benjamin Franklin, who gave us a lot of really interesting contributions. I'm not going to talk about the medical stuff, but the inventor of the bifocal reading glasses, which is amazing. And then, of course, this work with electricity. Unfortunately, he got it a little bit backward. So we call the positive terminal the anode because that's without the negatives, and the negative terminal is the cathode. But in terms of current flow, Franklin was assuming that charge flow was going from plus to negative, but really we know that electrons flow from negative to positive. So we're always going to dance around this issue about what we call conventional current and electron flow. So even though it's electrons that are flowing through these conductive wires, we could also conceive of it as being electron holes that are positive flowing in the other direction. Now, when we try and look at the connection between current flow and voltage, we recognize that voltage is sort of like pressure. So imagine if you took a pail and you drilled a hole in the bottom of the pail, and then could picture after we fill up the pail with water, we try and picture how fast that water is going to shoot out. Maybe we drill a hole in from the side so it shoots out sideways. So initially, the water is going to shoot out really quickly, but as the depth of the water decreases, then the velocity of the water that's shooting out is going to decrease. So the same thing is true with our potential difference. If we have a big potential difference, then the charges are going to be able to go faster through whatever is holding them up, through whatever resistance is there. So the proportionality constant between voltage and current is called resistance. And this actually is a pretty good sim, so I'm going to just take a look at it. I don't know if this is the link that's live. Hang on. No, it doesn't want to link. I'm going to open a new tab, and I think you'll still be able to see it. I don't think this URL is going to work because I need to get rid of the slashes in the beginning. Actually, that'll work. And this is an HTML5 sim, so I can run it across many different platforms. All right, so I'm looking at a simulation. Give it a shout if you can't see it. No shouting, great. Okay, so in this simulation, we get an idea about the difference between conventional current. And that's what we're seeing, these blue dots, is conventional current going from negative to positive. Now let's take a look at the voltage calculation and see how we're doing. So in sort of in black here, and it doesn't stand out particularly well, but it's counting the number of electrons that are doing their thing. And so we have a connecting wire or a resistor, and that's holding back the current flow. And here's where we're doing a little bit of work, little bit of useful work. And so this is an important difference between measuring current and measuring voltage, which we're going to focus on Tuesday night. The way that we measure current and the way that we measure voltage are fundamentally different. And that's because when we're measuring a voltage, we're looking at a potential difference between 2 points in our circuit. But when you're measuring current, you're counting the charges as they move past a given point. So ammeters always have to be in series and voltmeters always have to be in parallel. It's definitely a big idea. All right, well, let's do the obvious. We'll turn up the voltage and see what happens. And you can see that the resistor is getting warm now. So the conduction electrons inside the resistor are flowing okay, but they're having energy sharing collisions with some of the other molecules are in the resistance. And when it gets hotter, then they move back and forth faster. So it actually offers up more resistance. Resistance increases as the device gets hotter. The classic incandescent light bulb features current flowing through a wire that's very, very small. And so it gets hot, and it gets hot to the point of glowing. Now that we've cranked up the voltage, let's turn up the resistance and see how does our stimulation represent increased resistance. Well, you can see there are more green dots in here. So there are more things to get in the way and have energy sharing collisions, which reduces the overall speed of the charges as they move through the resistance. The average speed at which they move through is called drift velocity. You can see they're kind of drifting, the blues are sort of drifting through the greens. Okay, good. I want to take this now. I've got voltage all the way up and I've got resistance all the way up. Let me start backing this down. Oh my. Right, so it's quite hot, and actually this could potentially start a fire. So this would be what we call a short circuit, where there's almost no resistance. And so the battery is pumping up charges just as fast as it can be, but like I said, it's getting kind of hot. All right, let's go back and take a look at our notes again then. And so we've already introduced this as Ohm's law. Now, if we plotted voltage as a function of current, then we would get a straight line. What we're going to do when I see you on Tuesdays, we are going to do that, but our vertical axis is going to be voltage and our horizontal axis will be current. And then the slope is going to be the resistance, not 1/R. That was kind of cheap. And the unit for resistance is the Greek letter omega for ohms, named after a German physicist named Simon. So we're going to talk about resistance here in a minute, but I think now's a good time for us to do a couple of practice problems. So I'm going to, if you haven't had a chance to open up the agenda, then I'll just leave it here for a second so you can take a screenshot and see what we have for practice problems. Not too much, huh? And these are going to go really quickly. Okay, so I'm going to stop my share and then change cameras and go to my whiteboard cam. Yay. Yeah, we see lots of charging stations popping up around, some parking garages and outside supermarkets and at rest stops on the highway. So Tesla claims that you can easily drive across the country, and if you use their charging stations, then you can drive across the country and you don't even have to pay for electricity. So it's a bold claim, but nonetheless. However, it is important to recognize the fact that the faster you go, this is a dual temptation for electric car drivers, because they have incredible acceleration. So there's really no vehicle that's going to accelerate faster than an electric vehicle. But the faster you go, then your battery performance really tails off. So going 75 miles an hour in a Tesla is not going to get you where you want to go. All right, well, anyway, 6.7 amps for 5 hours. What do we got? So let's imagine it's a charging station. And we deliver 6.7 amperes. Make that decimal point a little bit bigger. And over 5 hours, how much charge are we talking about? So charge is equal to the rate at which current flows. So if I take current and I multiply by time, then that's going to tell me the total amount of charge. And so 6.7 amps, those are definitely the correct units for current, but hours is the wrong unit for time. We need the SI units for time. So I can still put in hours here. And I'll write down units since I am going to do some dimensional analysis with 5 hours. So I need to convert hours into seconds so that when I multiply these out, the seconds are going to cancel. So 1 hour is 3,600 seconds. And that's it. That's the only twist here. Just going to grab a calculator really quick. And I would encourage you to just try and do the math yourself too. So we get a lot of charge flow. And we get 1.21 times 10 to the 5th. Coulombs. Looking pretty good. Okay, how about a hair dryer? 7.5 amps when plugged into a 120 volt line. What's its resistance and how much charge in 15 minutes? So a hair dryer. We have 120 volts and then 7.5 amps. This is actually a good thing to talk about too, because if you've ever had a circuit breaker pop off on you, a hair dryer is actually a pretty big consumer. It's not typically on for very long. But while it's on, it draws a lot of current, and so does a microwave. So a 1500 watt microwave might draw this much current or maybe even more. So if you did a hair dryer and a microwave at the same time, I don't know how many people are making breakfast and drying their hair at the same time, but it could happen. And that it's quite likely that this would trip a circuit breaker. Because even though the wires inside your apartment or your house are pretty robust, they do have limits. And we saw before when wires carry too much current, then they can get hot and and potentially start a fire. So to preserve that, we have circuit breakers that when the current exceeds the maximum safe rating for our household wires, then it trips and interrupts the circuit. And then you can't do anything with that circuit until you go back, fix the problem, and then reset the breaker. That's sort of like a intermediate. So back in the day, we used to have fuses that would burn right through like a light bulb. And then you'd have to actually replace the fuse, and it means you'd have to have extra fuses on hand. All right. So we're supposed to find the resistance. Here's Ohm's law. If you remember that we had that graphic formula before for Ohm's law. I never use this very much, but some people like it. I'm looking for R. So R is going to be equal to V over I. And I'm going to do 120 volts over 7.5 amps. And those are both SI units. So I'm in good shape with those. So that's pretty straightforward. And of course, we've done a lot of this in the past. And so I get 16 ohms. So this is a little counterintuitive. If we multiply these two numbers together, we can find out the power of this hairdryer. So if you were out shopping for a hairdryer, maybe as a present or something like that, one of the features you'd be looking at is power, because this would translate to the rate at which it delivers heat. So a more powerful hairdryer is going to have a higher power rating. And I got this number by just multiplying these two together. So we can see the relationship. This 900 watts is going to have a resistance of 16 ohms. That's because everything's plugged into 120 volts. So reporting out on the power is also an implicit way of telling us what the resistance is for this device. Okay, so I'm looking for a volunteer here. If somebody could unmute and then give me, like, what's an extreme hair dryer? How much power are we talking about? If you're not sure, just throw something out there. Okay. All right, let's suppose a real hair singer. Let's suppose we had a 1500 watt hair dryer. So if we go through the math in this case, then we would reverse engineer this. So first of all, the 1500 watt hair dryer is going to draw more current. So I would be equal to P over V. So that's 1500 divided by 120. And I know this is not asked for us in the problem, but I did want to illustrate an important point that's slightly counterintuitive. So this monster hairdryer is going to draw 12.5 amps. So when it's plugged into 120, it draws much more current. And that means its resistance, which is equal to V over I. So then 120 over 12.5 is going to be a smaller resistance. So that's the counterintuitive part that I was talking about. Yeah, so this is going to be 9.6 ohms. So the point is, if you have an electrical appliance and you want a more powerful one, then in your design, you're actually going to make it have less resistance. And that's why you hear people using the term draws more current. So when you plug it in, we assume that all the plugs are at 120 volts, and given that resistance, it's going to pull 12.5 amps rather than the 7.45 that we saw before. The other part of this calculation is going to ask us to do the total amount of charge that flows in 15 minutes. So again, that's the combination of these two numbers with a little bit of dimensional analysis. So Q equals I times T. And so this is going to be 7.5 amperes times 15 minutes. But then doing a little dimensional analysis, of course, there are 60 seconds per minute. Right, and then I'll have coulombs when I'm all done. Okay, so 6,750. Coulombs. Okay. I'm going to change cameras again. And just a quick check-in to see if there are any questions.
So far, so good.
Okay, thanks, James. All right, I'm going to change cameras then. All right, and then I'm going to go to share screen again. Okay, let's take a look at our notes and see where we left off. Here's my slide deck. So now we're going to start talking about devices in particular that are especially designed to show resistance. And I get to show you a toy too. I'm really excited about this. So let's see, let me make sure I've got all my goodies in place. I'm going to do a little desktop demonstration for you. And hang on a minute. Okay. Okay, good. I'm just getting some props ready. So I hope you like it. All right. And I'm going to introduce a couple of devices that you're going to use on Tuesday anyway. And then we'll see them again on Thursday too. I'll do a couple more demonstrations. All right, so what is a resistor? And the idea is that we need to control this electric current. So we've got charges with potential energy. And if we let them just run, then bad things could happen. Because if there's low resistance, then they run real fast and we get a lot of power. And one thing the utility company is doing is that they are guaranteeing that all the charges we get are going to have 120 units of potential energy. But what they also, and it's a business, so they're also quite happy to deliver as much current as you want. And that's where bad things can happen. So we need resistance in our lives in order to slow down the flow of current. That's their primary job. And there's a color code here that we're going to use, but it's not something you have to memorize. And of course, there are color code converters. So you can find a number of apps online. And I have an app on my phone too that does it, although I know most of them by heart now. But here's how the color code works. So these resistors are really small, and I'll show you some in a second, but they're too small to actually write anything on. So by using color codes, we can translate this to whatever the value happens to be. So we need 10 digits altogether. So we use the colors black, brown, and then the colors of the rainbow, but that's still not enough. So we have to throw gray and white in there too. And between all of those, that gives us 10 digits. And then resistors are manufactured by the billions. In fact, there are probably more resistors in the world right now than there are leaves on trees. And they show up in all our devices. So phones and laptops and a bunch of different applications for resistors. So the way we can represent a resistance with 2 degrees of precision is that we use 2 colors to represent a value, a numerical value, a third color to represent an order of magnitude, and then a fourth color to indicate a tolerance. So most of the time we see gold. Gold means 5%. So that means if I read the color value off the resistor and figure out what the number is, then the actual resistance is going to be plus or minus 5%. Okay, so let's do an example. I'm going to stop share, but you probably want to have this up when I do this. So it'd be good for you to have this color code. And then I'm going to change cameras, and I'm going to bring my document camera down from pointing at the whiteboard to pointing at my desktop instead. So hold on, this is going to be a wild ride. Here we go. Boom. You're getting to see my porch area here. All right, so I'm going to point this down. And I'm not sure how close we're going to be able to get for this, but here's an example of a resistor. Actually, there are 2 of them. And there's my, my enormous index finger next to them to give you a sense of scale. So they're really small. So I'm curious if we will be able to get in there close enough to be able to see this. So let's make sure we've, yeah, the blue package is probably not going to be big enough for you to see. Let me throw in another one here. So this is a little bit larger. All right. And I'm going to turn, I have a bright desk light. I'm going to turn that off and maybe that helps. I don't know. Okay. So first of all, why 2 different packages? Why is one bigger than the other? Oh, this one's easy to see too. Try that. Yeah. So this is a 1/4 watt package right here. This little one and this one and this one. They're all 1/4 watt packages. This blue one is actually a metal strip resistor. So there's a metal strip inside this casing, and that's what's guaranteed. These tend to be a little bit more accurate. These are carbon film resistors. And they're all in a smaller package compared to this one because it's based on what the application is going to be. Because when current goes through the resistor, it steals a little bit of power. It steals a little bit of power as P equals I squared R. So that's a loss that's going to be here, which makes sense. So if you're having energy sharing collisions, and that's what slows the current flow down, then that energy has to go somewhere. So these are rated at 1/4 of a watt, a 1/4 watt, and this one is rated at 1/2 a watt. So this one can take more current. And that's an interesting calculation. So you can figure out what's the maximum amount of current that I can run through here without it burning up. So I think that you can see this one. And the colors on this one are brown. I'm going to just jot this down on a piece of paper somewhere. Oops, I got a whiteboard here. And you might want to try this too. So if you've just got a piece of paper handy, we'll just write down what the colors are, and I can show you how we can use this to figure out what the value is. So I'm taking a look at this, and first of all, we have to figure out which way to read it. So I have gold here, black, red, and I think that's brown. Let's call it brown. So that's our first challenge, is to figure out which way to read this. Okay, I'm gonna zoom out a little bit and then come in with the giant hand. Okay, so here's my whiteboard. And what I mentioned before is that the colors are brown. I know this is blue, but brown, red, black, and gold. Now, how come I didn't read it the other way? It's gold, black, red, and brown. Well, there's definitely a reason for it. So if you take a look at that slide that has the resistance values on it, then you can see that the gold is the tolerance. So that represents 5%, really plus or minus 5%. And then I can interpret the code for the others. So black has a value of 0, and brown has a value of 1, and red has a value of 2. All right, well, when I put this package together then, the way we interpret it is that I have 2 significant digits, and then I have a multiplier times 10 to the blank. So now I can fill this in. The multiplier is 0, and the 2 significant digits are a 1 and a 2. A 1 and a 2. And then I go with black, which is 10 to the 0. So 10 to the 0th is just 1. So this code cooks down as 12 ohms.
You might have to move it over just a little bit. I don't know if it's to your, yeah, thank you.
You got it. Have to focus too. Thanks. Okay, good. And then I want to see what you're seeing here. So I'm just gonna put zoom here. I think this is actually upside down. Whoa. There we go. A little bit better. All right. Does that make sense? Why don't you try and do one on your own? I'm just going to write down some resistor values. So let's suppose that I'm just going to erase this and do another template. Let's suppose that I have one that says red, 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 gold. So I can leave the gold there, but now it's red, red, red. Okay, why don't you take 30 seconds and see if you can decode this? What would be the value? And why don't you put your answer in the chat? Thanks, James. Just to help out with my self-esteem. Is there anybody out there? Two, 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 2 times 10 to the second power, also known as 100. So this is 22 times 100. Or if you want to do it like the cool kids do, they say 2.2K ohms. Yeah. All right. Can I just see a little thumbs up action, if that makes sense to you? You can use the reactions in down the bottom. Okay. Yay. All right, now what I'd like to do is to give you a value for a resistance and then see if you can come up with the colors. Zutolor. Okay. So two 2.7 mega ohms. And mega is 10 to the 6th power. So what you should do is remember that there's no decimal point between the colors. So you probably want to think about this is 27 times what power of 10. And then see if you can do the color code. And it would be awesome if you could write the colors in the chat.
I guess it doesn't matter, but what tolerance?
Yeah, almost. We would never see anything different than 5%.
Okay.
That was a good clarifying question, though. Thank you. So this would be a very pretty one. And let's see if we got some winners here. Yeah, interesting about the order of things, right? So, so here are what the numbers turn out to be. So I'm writing this so there's no decimal point. So 27 times 10 to the 5th. So we need the color for 2, which comes first, and then 7, and then 5. Yes, red, violet, and green. And you know, you could say purple instead of violet, but they're trying to do the Roy G. Biv thing with the colors. And if you're colorblind, then forget about it. But ladies don't have to worry about that because there's hardly any color blindness in women. Almost all men. 10% of men, I think, something like that, or some degree of colorblind. But your carriers, it's one of those XY recessive genes. All right, so that's cool. Now here's what I wanted to show you really quick. So toys. Oh, red does not erase. Oh no. All right. So I'm going to just expand this view a little bit for me. And then here's what we have for new toys. So I wanted to talk about this breadboard for a second. And I'll zoom in. So I got too many wires here. Okay, so we'll zoom in a little bit. That looks pretty good. All right, so this is one of the little gadgets I got for your kids. So when you show up on Tuesday, you're gonna have one of these things. But I still have to do a little bit of work on it to make it a little user-friendly. But it's a voltmeter. You remember those big meters that we had? And this is a tiny voltmeter that I found online, and it goes for $3. $3 each, and I was just so happy. So you're all gonna have one of these to take a look at. Now with my breadboard, that when I take a look at how it's laid out, I'm going to see if I can zoom in one more time. Good. And I know you don't have yours in front of you right now, but just to point out some features, and this is just going to help front load things for next Tuesday. So I have a plus and a minus here, and then there's a red line that goes all the way down. And this is telling me that all of these are connected. I have little sockets right here. So if I wanted to connect something, all I'd have to do is stick one of these hookup wires into the breadboard. And then this black one, it says minus. So all of these holes are ground. Now over here, I have numbers next to rows, 1, 2, 3, 4, 5. And the numbers correspond to these sets of 5 holes. And then the 5 holes are labeled as A, B, C, D, and E. So just like bingo or battleship or whatever, I can call out and I'll say, okay, use 2A to connect 2 wires together. Now what I'm going to connect together is I'm going to use these 2 resistors. So if I'm going to connect 2 resistors together, here's what I can do. I start off, I'm going to zoom in a little bit so we can see. My big fingers in the way. All right, so I'm going to take this resistor and I'm going to bend it like it's a croquet wicket. Like that. Okay, and then I'll be able to stick them, and I'm going to use, I'll use 1E and, come on fingers, 1E and 7E. I'm just looking for whichever hole it just drops down into nice and neat. Okay, good. All right, and then I'm going to take another resistor, and I think this is going to be a good choice. So I'm going to drop that into, remember I had used 7E, so I'm going to put this into 7D, and now those 2 resistors are connected together. I'm going to use 7D and 13D. So these 2 resistors are now electrically connected to each other right here. Now I'm going to take a short hookup wire and I'm going to connect, I'll fold them over so you can see a little bit better. There we go. And I'm going to put a hookup wire in next to that, and that goes into ground. And then I'm going to take another hookup wire and connect the other side to positive. There we go. And then I'm going to put that in row 1. And so now I have current flowing. Charge flow is going into this top resistor and then through it, and then coming out the bottom, and then going back to ground. So now I can take my new voltmeter, and it's just saying 0 right now. And I can probe and see what I get for values. So here I'm getting 4.7 volts. And then I can jump down to here, and I get 2.3. And then I go here and I get 0. So again, in our distribution charge model, I've got Amazon trucks coming into the circuit, and they're loaded up with 4.7 packages each. And they drop off some of the packages here, and then they're left with 2.3. So that means 2.4 volts happened here. And 2.3 and 2.4 are almost the same thing. Or another way of thinking about it is that 2.3 is almost Yeah, I got 4.6 there for a minute. So 2.3 is half of 4.6. So these two resistors are actually equal to each other. They have the same resistance. Okay. Well, that was just a quick example about how to use resistors. Now, how do you get the resistors to have different values in the first place? I'm going to change cameras again and then go to share screen and take a look at our notes. Okay, so there again, just some definitions here in this one. So resistivity is one of the keys for us to be able to create different concoctions to get different resistances. Because resistivity is a property of the material, and it's not really a particular value of resistance. It's one of the indicators. So resistivity is right here. It's the Greek letter rho. And then we also have L and A. So L corresponds to the length of some device, and A corresponds to cross-sectional area. So we've all seen that simulation that I introduced you before. And you can imagine a resistor as sort of like a pipe. So area refers to how big the opening is for the pipe. And then L is the length that charges are going to be exposed to energy sharing collisions. So the longer the pipe, the more resistance there's going to be. But then resistivity is going to tell us how the material itself is going to be populated with things that are ready for energy sharing collisions. So here's some resistivity values, and we measured resistance of your skin when our first hybrid session. You can see that good conductors are all metals, of course. They're also good conductors of heat. We talked about that before, because conduction electrons are the primary vehicle for thermal conduction as well. And copper is very good. Silver is better, but more expensive. Copper is actually getting very expensive too. We're seeing the market really shoot up these days with the price of metals. So I often, I'm buying raw material, and yeah, it's getting very expensive. So gold is a pretty good conductor too. Aluminum, a little bit worse than gold, but obviously gold is very expensive too. Although when you buy fancy audio equipment, you might see they're sort of like gold tipped. It's not real gold, but they're doing that because, copper would be better. The advantage of gold over copper is that gold doesn't tarnish. But anyway, and then they start to get better. Now, tungsten is what was the filament that was used in the incandescent light bulb, and it's long time iterations. And it's not as good a conductor, but that's on purpose. So since it has more resistance, then when you run current through it, it's going to start to glow. It'll glow red hot. Then we also have this temperature coefficient too, so we want to keep that in mind. But insulators, of course, are going to have many orders of magnitude higher resistivities because they're not that great. And here's how we deal with temperature. So we start off with sort of a base resistivity, and then for every degree above room temperature and degrees Celsius, then we would multiply by this coefficient and then add it to the resistivity. So that's what the temperature coefficient is. If you take a look at the previous slide, here they are. All right, so I'm going to stop share. No, I think this will work because I'm just going to look at a new tab. Okay, so scream something if you can't see this problem. What? That's the last problem for tonight? Joe, are you serious? What's the diameter of a 1 meter length of tungsten wire whose resistance is 0.32 ohms? Okay, gotcha. So you might want to stay on that slide that's got resistivity on it, but I'm going to stop sharing and then switch over to the camera that points at the whiteboard. Oops. It's upside down. Better. Turn this light off to cut down on the glare. Yes. And a little bit of focus. Still a little tilted. Okay, that looks good. Okay. So just as an aside while I'm setting this up, that you can, I'm going to offer up a link to Mastering Physics. When I was taking a look at it yesterday, not everybody has an active link on that. So just as a reminder, you should have had access codes sent to you back in early September. And for the first couple of weeks, I'll have this as an option that you can use to submit problems, because you'll probably find it a little bit easier to use Mastering Physics. And I'm going to kind of take it easy with that because it's new to me as well. And I don't want to turn it into a real high stakes thing. So, but if it works for you, some of you have used like Mastering Chemistry and some other classes before too. So again, so I'll roll that out. You'll see links showing up in Canvas by the end of the week, or actually probably tomorrow. And then you can use those links in order to do practice problems, or you can continue to use the practice problems that are on Canvas right now. Excuse me, that's up to you. So we're going to walk into it sort of in a trial mode, and then we'll get a little more serious as things progress. I'm not too interested in changing assessment techniques yet. So quizzes are going to continue to be on Canvas with essay questions and then submit with one upload file. All right, so 1 meter length of tungsten wire and the resistance is 0.32 ohms. One meter tungsten on 0.32 ohms, and we want to find A. Cross-sectional area. So again, here's our pipe, cross-sectional area. And the length is 1 meter. And resistance is equal to resistivity times the length divided by the cross-sectional area. And for tungsten, resistivity is going to be equal to, so we can look that up. I think it was 5 point something. Yeah, 5.6 times 10 to the minus 8. Ohms times meters. Well, we can go ahead and take a look, but we should probably rearrange it to solve for acceleration. I mean, not acceleration, wow. Guess what I was teaching today. So multiply both sides by A and divide both sides by R. So A is equal to resistivity times length over R. Good, and of course we're looking at very small numbers here, so we want to be careful and use scientific notation on a calculator. So 5.6 E minus H, and then times the length, which is 1, and then divide by the resistance, which is 0.32. All right, so let me just write those up here on the board really quick. 5.6 times 10 to the minus 8, and then 1 in the numerator and 0.32. In the denominator. Now, actually, I believe this problem asks us for the denominator, or the diameter. What are words? Okay, so I'm looking for diameter, but this will tell me what the area is, so that's a good start. And so this is a very small number, 1.75, but of course we're talking about wires, so of course they're going to have a very small cross-sectional area, times 10 to the minus 7, and this is in square meters. So remember, a square meter is a very big unit. The area of this whiteboard is probably close to a square meter. Okay, so we're almost there, but we still have to find diameter. Now, the way I would do diameter is I could go pi r squared, but then I have to remember to multiply r by 2. So you could do it this way, pi d squared over 4 equals 1.75 times 10 to the minus 7. So the sequence of events is going to be multiply both sides by 4, divide both sides by pi, and then take the square root. Okay, great. And why don't you throw that into the chat when you get an answer, and we'll see how we do. And the answer you get from this is in meters, of course. So when you put it in the chat, why don't you put it in millimeters so we can see what it looks like without exponents. So see if you can express your answer in millimeters. So I have not seen a correct answer in millimeters yet. Yeah, that's right. I got 0.47. So half a millimeter thick. That sounds about right. Okay. Good. I'm going to stop recording now. That's the end of the new material.